Hey everybody, nice to imagine seeing you even though I can't see you. I hope everyone is doing well. Um, Here is the second chemistry supplement. These supplements are a chance for me to do a little bit of chemistry background that will help inform the food science content that we'll be talking about. So, I'm going to talk about a little bit of organic chemistry today. Organic simply meaning carbon containing, carbon based chemistry. But I'm going to do it within the context of a discussion around kombucha. So, supplement two, the chemistry of kombucha, but the chemistry part first. Dang, what is that crazy looking molecule? That is a big beast of a molecule. We're going to find out what it is and how to make it real soon. Hold on to your hats. The first little piece that we're going to need to build to put this giant puzzle together is an understanding of a chemical group called an alcohol. Now, when people say alcohol, they think of the stuff you drink or maybe the stuff that you rub on a cut or something like that, rubbing alcohol. Um, they may think that they're the same thing. They may not really understand. An alcohol is any organic, meaning carbon containing compound, in which there is one or more what are called hydroxyl groups. These are OH groups where the oxygen is attached to the hydrogen and also to a carbon atom. So this schematic I have, this molecular drawing on the left-hand side here, R with a line to an O with a line to an H. The R can be anything, any kind of R group, any kind of organic molecule that you want. So I depicted three common alcohols right here. There is methanol, which is so called because it's like methane, CH4, except one of the H's is replaced by an OH or a hydroxyl group. Methanol is the alcohol that is in the liqueur absinthe that makes it have its unique properties. Ethanol consumed in too great of a quantity is quite toxic and will actually make you go blind. They believe that this is the reason that Van Gogh painted such psychedelic paintings. Some of his paintings were so psychedelic was because he was suffering from methanol poisoning from his consumption of absinthe. Regular drinking alcohol, ethanol, that would be in any other kind of alcoholic beverage, is like ethane, two-carbon chain, with one of the hydrogens on that carbon chain replaced by the alcohol group. So that's ethanol there, CH3, CH2OH. Rubbing alcohol, isopropyl, it is a propyl group, meaning a three-carbon chain, and the iso simply refers to the fact that the hydroxyl group is on the central carbon, sort of isometrically positioned within the molecule from equal distant from either end of the molecule. So isopropyl alcohol. It's a type of propanol. All right. So that's an alcohol group. The next chemical functional group, chemical functionality that I want to discuss, to introduce to you, is the idea of a carbonyl group. A carbonyl group is like an alcohol group, except that it's been a little bit more oxidized. The oxygen is double bonded to a carbon instead of single bonded with the other bond going to an H. So it's kind of similar. It's an oxygen bound to a carbon, except it's a double bond. Carbonyl groups are extremely common in all different types of organic compounds. They're common within various classes of larger functional groups, as we'll see later in the semester. Actually, in a little bit as well. So here is a common example, acetone, the stuff that is in nail polish remover. It looks like isopropyl alcohol, except the CO is a C double bond O rather than a CO bonded to an H. So it's a carbonyl group rather than an alcohol group. All right. So we can take those two functional groups, the alcohol and the hydroxyl group and the carbonyl group, and when they are each attached to the same carbon, we get something called a carboxylic acid. All right, so a carboxylic acid is an organic, meaning carbon-based acid that has the carboxyl group, the carbonyl, and the hydroxyl group, the OH. So the two simplest forms of carboxylic acid are vinegar, which has two carbons in it, and formic acid. So acetic acid, or common white vinegar, is that molecular formula that you see below right there. And then formic acid is even smaller. It's just a single carbon where the fourth bond the carbon can form is actually just to a hydrogen. So formic acid is often added as an antimicrobial agent to cattle feed. It's not overly toxic to them at all, and it prevents the cattle feed from spoiling. So you may be asking yourself, what the heck is an acid? Well, an acid is any molecule, for the purposes of this class at least. There are more sophisticated definitions of acid that become necessary in certain contexts, but for the purposes of this class, pretty much the only acids we're really going to be talking about, we will talk about hydrochloric acid when we talk about stomach acid, but otherwise pretty much every other acid is going to be some kind of a carboxylic acid. And these carboxylic acids, any acid for us is going to be some kind of a proton donor, some molecule that's able to give up a proton and ionize itself. So in carboxylic acids, because that carbonyl group is attached to the same carbon that the hydroxyl group is on, that carbonyl group activates that alcohol group and turns that alcohol group kind of acidic. Makes it so that the oxygen that's attached to the hydrogen in the hydroxyl group is willing to ionize itself. All right, and we're going to see how that works right now. The electrons that form the bond, we talked about this in the first supplement, the electrons that form the bond between an oxygen and a hydrogen, in this case, are going to flow towards the oxygen because the oxygen is what's called a more electronegative element. Simply means it's greedier, it's hungrier for the oxygens. It wants to pull oxygens to itself. It's happier being surrounded by oxygens. By electrons than the hydrogen is. All right. So the first step in this carboxylic acid, being an acid, is going to be donating the hydrogen. Those electrons that are between the bond flow towards the oxygen, and it's in equilibrium, meaning a back and forth process or reaction, where that hydrogen has now been liberated and it's had some electrons taken away from it, and because of that, it has a positive charge. The proton in the nucleus of the hydrogen doesn't have any, it's positively charged, and it doesn't have any electrons directly around it in its orbit to balance that positive charge, so it has a formal charge of +1, And the oxygen that tore those electrons away from the hydrogen is carrying an extra electron. It got one from the hydrogen that wasn't originally its electron. So it has a negative charge. All right. And this ion, we call that a carboxylate ion. Before it was a carboxylic acid. It was ready to donate a proton. Now it's a carboxylate ion. This carboxylate ion, the reason it likes to be in this form is because it's particularly stable. And it's stable because this negative charge that is on the oxygen, that oxygen doesn't have to carry it all by itself. It's able to spread those electrons out into the bond that it has with the carbon and sort of push electrons away from the carbon on the other double bond O. And it is in resonate. It's in this resonant form, or this equilibrium back and forth, where the two oxygens are sort of co-sharing that single negative charge. So neither bond is exactly a double bond or a single bond. It's somewhere, the reality is it's somewhere in between. Both of those CO bonds are like 1.5 bonds, if you want to think of it that way. Anyways, that's the carboxylate ion, and this is why carboxylic acids happen, because they are particularly stable. You may be thinking, what does this have to do with food? It's like all over the place. Acids are one of the fundamental aspects of cooking chemistry, and it's pretty important that we understand how these work so we can have other discussions. All right, so I'm going to take one more step in chemistry here with you in a reaction, and that is the reaction now of a carboxylic acid that we've built up with an alcohol. A carboxylic acid and an alcohol, two different molecules, they can actually interact with one another through what we will call a dehydration reaction to form what's called an ester. And it's a way of linking two molecules together. Carboxylic acid and an alcohol can combine to form a single molecule called an ester. So in this depiction here, we have a carboxylic acid that has some R group on it, some sort of carbon-containing R group, and then the alcohol has some other R group. It can be anything, any kind of long chain or weird big structure. Doesn't matter what the R group is. You just have to have a carboxylic acid and an alcohol. And we pull water out, and we form, so we're pulling the water out. This is why we call it a dehydration reaction. And the R2 from the alcohol is now attached to the oxygen bridge with the carbon of the carboxylic acid. This reaction, it's actually one of the last chemical reaction mechanisms we're going to need to talk about this semester. But we do need to talk about it because it's so important to so much chemistry that happens in food and in our physiology, etc. All right, so that's the formation of an ester. The last category of molecule is an entirely different kind of thing. There's no oxygens involved here. This is the category called aromatic molecules. Now, the most simple or most fundamental aromatic molecule is called benzene. It is a 6-carbon it's a 6-carbon chain that's actually in a ring. It's a hexagon of carbons that each is attached to a hydrogen. So it's C6H6 is the empirical formula for benzene. And benzene is a very stable molecule. It's an exceptionally stable molecule for a couple reasons. The primary reason being that there is resonance stabilization as well here. Those C double bond alternating with C single bond C, etc. in this chain those double bonds and those single bonds, the electrons can flow from one double bond into the adjacent single bond, and so on. And in fact, none of the carbon-carbon bonds are really the length of a double bond, nor the length of a single bond. It's somewhere in between. In fact, all of them, these carbons, are all like 1.5 bonds in length from each other. And so often when you see a benzene ring drawn, you see it as this hexagon with a circle in it to sort of imply that the electrons in the bonds that are holding the carbons together are sort of circling around one another and being shared in this sort of ring, this benzene ring. This was first discovered by this dude on the right-hand side here, August Kekule, who was a German chemist that lived in the 19th century. And he had the empirical formula for benzene. He knew that it was C6H6, but he couldn't figure out for the life of him what the structure was. And he had drawn it this way. Was it the diagram on the right, or was it the diagram on the left? And he had been working and probably not sleeping enough and definitely sniffing way too much benzene fumes, I would guess. And so he had a kind of a fever, the story goes, he had a kind of feverish dream one night where he dreamt of Ouroboros, the mythic snake, eating its tail from ancient times, and meant to sort of signify infinity and the eternality of life and death. The snake, constantly hungering, but then eating itself at the same time, so building and destroying, the sort of dichotomy. It was kind of like the yin-yang symbol of ancient times. So he dreamed of the Ouroboros. He had this fever dream of the snake chasing its tail, and said, "Aha! This is what the structure of benzene was." He felt that he had found some really profound thing, and he had, in fact. All right, so the benzene ring. So I've shown you alcohol groups, carbonyl groups, carboxylic acids, esters, and aromatic molecules that are some variation on a benzene ring. So that's 5 different things I've shown you in short order here. That's like most of the semester of organic chemistry boiled down, and only so that I can help with the second part of supplement 2. On to the kombucha. We're going to see how all of this relates to kombucha. So for those of you not familiar with kombucha, pretty popular thing. Probably most of you have tried kombucha of some sort at this point. It's pretty common to find it in the refrigerator section of your produce aisle, in any grocery store where they have several different types of kombucha that you can buy, often flavored ginger or strawberry, peach, whatever, blue Bernie, if that's your favorite flavor. In 2019, now I don't know the statistic for 2020 because what a year that was, but the market share for kombucha in fermented beverages was over $1 billion. That's a lot of money. That's a lot of kombucha. Considering that when I was your age, not that long ago, kombucha was an incredibly niche beverage that very few people had ever heard of. It's grown in popularity dramatically since that time. So in 2019, last year, for which there are reliable data, it was $1 billion of kombucha were sold. That's quite a bit. All right, so what is this stuff? Pretty freaking simple. The most basic recipe for kombucha, you just need black, or if you want, green tea. Green tea works. Mix some tea, stick some sugar in it, and stick in the kombucha SCOBY pellicle. Huh? Yeah, SCOBY, symbiotic culture of bacteria and yeast. So That snotty, scuzzy, kind of beautiful, in my opinion, looking mess there in the jar is some SCOBY. That is the culture that has bacteria and yeast in it that are in symbiosis, or a mutually beneficial working relationship. The word pellicle simply means the mat that you see, and then the SCOBY is the combined culture of the two microorganisms. Actually, whole communities, various sorts of bacteria and yeast that are living in the kombucha. Okay, so that's the basic ingredients. You can add all kinds of flavors and et cetera, but that's all you need right there. So let's get into the chemistry of it. Holy smokes, look at that. Plants, such as tea leaves, often build these huge molecules from those very simple building blocks that I showed you earlier in the talk. The hydroxyl groups. If you look at this molecule, you'll see hydroxyl groups, you'll see carbonyls, you'll see carboxylic acids, you'll see esters. There's lots of esters in there. You'll see aromatic molecules all over the place. This giant molecule is actually just a fragment of a far larger continuum that looks much the same as this, called lignin. Lignin is one of the structural components that you find in plant material, particularly leaves. And you certainly find lignin in a tea leaf. Well, when you harvest the tea leaves, dry them, and then roast them, that releases fragments of this that we call tannins. These tannins, also pretty giant, crazy-looking molecules. This you may recognize from the first slide of the presentation. This tannin has all kinds of aromatic molecules in it. You'll see lots of hydroxyl groups. You'll see lots of esters with carbonyl groups in them. This is a tannin. All right. So what is a tannin? Well, a tannin, because of all these aromatic compounds often are colored because they absorb light in the visible spectrum. And these tannins are the color-containing molecules that are in tea. They can stain a tea mug. If you let a tea mug sit on the side of your bed table, I'm sure you haven't, because nobody in this class would ever do that, of course. I'm sure you do your dishes as soon as you are done with them. But if you were to leave your tea mug sitting around, you would notice that there was scuzz. This is like colored remnant from the tea on the side of the mug. It also can stain your teeth. These are the tannins. These are also the compounds that can give wine their color. All right. So, turns out tannins are necessary for the growth of the SCOBY. And we're going to find out why. Here's a SCOBY saying, "You complete me, tannin. Yay, I love you." Right. So, here's a little bit of an experiment. And what this is showing is moving from left to right, we see an increasing steep time, right? So this is, the person makes the tea to make their kombucha out of, right? So you boil tea, you chuck some sugar in it, then let it cool down, stick your SCOBY in it, and see what happens. This person made some tea and let it steep for 5 minutes, let it steep for 2 hours, and then let it steep for 8 hours. And then in each of these cultures added, everything else was the same amount of sugar, same amount of SCOBY was added. But the longer the tea steeps, the more tannins get released by the tea. And clearly the tannins are super important for the SCOBY, because the longer the steep time, the greater the pellicle formation. That is the cellulosic mat that forms on the top of the kombucha, the SCOBY mat, so to speak. So that steep time dramatically affects the further growth of the SCOBY pellicle. right? And if you add not just a dash of the SCOBY broth, but you also chuck in a chunk of old pellicle from the culture, then you get an even further growth in the formation of a new pellicle. So let's see that quantitatively. This is the exact same thing, but looking now at the mass of the pellicle in grams, right? So we have in dark blue. This is I'm sorry, dark green. This is the mass of growth of new pellicle that happens, and you can see here for the steep time in the first column of 5 minutes, 2 hours, and then 2 hours plus a starter pellicle. So the starter pellicle is in light green, and it's added to the mass. But having that pellicle dramatically increases the growth of a new pellicle, but nothing influences it as much as having a long steep time, so a high concentration in tannins that have been extracted from the tea. Pretty interesting. So the way I make my kombucha, I like to actually boil my tea bags in the tea for, I don't know, 15, 20 minutes. And then I leave, and this is in the evening, and I'll just let it sit on the stove and cool down overnight. So I get at least 8 hours of steeping that way. And that works really well for me. I get nice, healthy, big, robust pellicle formation. All right. So Kakuli wants to know, and other inquiring minds, what do the scobies do with the tannins? Well, SCOBY replies, glad you asked. I make all sorts of organic acids out of it. Organic acids. Let's take a look. So here are a couple of the organic acids that are produced by the SCOBY. There's acetic acid. We've already seen that. Acetic acid is white vinegar. White vinegar, maybe somebody's parent or grandparent uses vinegar as a cleaning agent. It's a great way. It's an antimicrobial or a microbicidal compound. That's because most bacteria don't like living in acid. Turns out the bacteria in kombucha do, so they make it. It's a very powerful preservative and inhibits harmful bacteria. So we went through the structure already, and the molecule below it is called oxalic acid. Kind of similar to acetic acid, but it has 2 acid groups on it. It's only 2 carbons long, but each carbon has a carboxylic acid on it. This is a pretty effective preservative. Most bacteria, besides the stuff in the kombucha, most bacteria do not really like oxalic acid, but it is a acid that is produced in a metabolic chain in your cells. So it's been shown to encourage intracellular production of energy because of that. I'm not going to go into that in detail now, but these are a couple of the acids. The question was, I jumped the gun there. Where can you find these 2 molecular fragments in the tannin? Well, they're all over. My gosh, tannin's practically nothing but little fragments of acetic acid and oxalic acid. So you could clip these fragments off and through an oxidative process and form any of these fragments. So here's another one, lactic acid. All right. So lactic acid, most people have heard of it because it is the byproduct of anaerobic glycolysis. That means like when you're lifting weights or something like that, doing anaerobic activities, exercise, your muscles produce lactic acid. It's a byproduct of anaerobic glycolysis. Another name for that is called fermentation, actually, and we're going to see what I mean by that in a bit. But it's got 3 carbons in it, and it's necessary for the digestive system. It helps with blood circulation, and is really good for toning the bowels and preventing constipation, etc. Where do you see lactic acid in the tannin? Take a minute, look around. What do you see? Where can you see something that may be able to be a lactic acid? Well, I see them all right here. These are all fragments that could readily be oxidized into a lactic acid. All right. So the point is, these tannins are broken down into all kinds of organic acids that are going to serve the purpose of the SCOBY, and we'll see in a bit why. Here are a couple others. So the first is glucuronic acid. Glucuronic acid is probably the body's most important detoxifying molecule. All right. And we get glucuronic acid from the oxidation of glucose. Glucose is certainly in the sugar that needs to be in the tea for the SCOBY. The SCOBY simply oxidizes one of the carbons, the last carbon in the chain of glucose and the little tail that the glucose has there, to an acidic and carboxylic acid group and forms what's called glucuronic acid. That glucuronic acid is able to form a ester with any kind of toxin that your body may come in contact with, as long as it has a hydroxyl group on it. All right, which hydroxyl groups are super common. They're all over the place in all kinds of molecules. So the liver is able, when you drink the kombucha and absorb the glucuronic acid, the liver, which is the first in the chain to get anything that you absorb through your gut, and so it becomes the storehouse for a lot of toxins. It tries to sequester toxins from the rest of the body. The glucuronic acid that is in the kombucha is converted to an ester with the whatever toxic hydroxyl containing compound that you may have sitting in the liver. It gets combined as an ester with the glucuronic acid, and then that molecule, the glucuronic acid ester, is kind of like a tag that enables the kidneys. It goes into your blood. It makes that compound more soluble, goes into the blood, and then the kidneys recognize that tag and say, "Oh, okay, I can just get rid of this," and it flushes that toxin out into the urine. All right. Another compound that is a breakdown product of several different things that the kombucha is metabolizing is malic acid. Malic acid works the same way. So it has a couple different carboxylic acid groups. It can form an ester with any sort of toxin in the liver, and that molecule is now tagged for removal by the kidneys into the urine. So glucuronic acid, malic acid, really important compounds for helping detoxify the body from all kinds of organic compounds that you may come in contact with in your everyday life. That's like all kinds of plastics and herbicides and pesticides, various resins that you may get in contact with, or phenolic compounds. Phenolic compounds are aromatic benzene ring containing compounds. Phenol is actually quite toxic. So, but it's basically a benzene ring with a hydroxyl group on it. So if you turn benzene into an alcohol, these compounds are able to help remove those from the body. Quite a good thing. All right. So, and I'm just pointing out the ester formation as is an important part of that process. Okay. So Kukuli has seen the light. I see how good they are for humans, why is the SCOBY making all these acids? Well, our sage SCOBY here, the ancient 2,000-year-old culture, 2,000-year plus culture, says the bacteria such as Acetobacter, Glucoacetobacter, Commagatacebacter, and the wide variety of yeast such as Saccharomyces, etc., long list of different yeast that are in the SCOBY. They are what are called acidophiles, and that is simply an acid-loving microorganism, acidophilus, so acid-loving. This is in contrast to most other molds and bacteria, which are not acid-loving. So for them, making all these organic acids is a really great way to create an environment that excludes and that helps them compete for the resource that's there, all this awesome sugar. They found this tea that has all this sugar in it. They want the sugar so they can grow. They take the tannins in the tea, make all this acid out of the tannins so that they can kind of get the corner on all this. Let's see this in more detail. This is the symbiosis in symbiosis culture of bacteria and yeast. This is how they're working together. Let's look at the science behind it a little bit here. So we make some tea, we dump in some sugar. That sugar is, the scientific name is sucrose. The yeast that is in the SCOBY makes a protein called invertase. And it's great because the bacteria don't actually have access to this invertase. The yeast do. They have the genes to make invertase, and invertase is a molecule that's going to break up glucose and fructose, which are the two monosaccharides, the single sugars, from the disaccharide white table sugar, right? So glucose is blood sugar, fructose is fruit sugar, sucrose is table sugar, it's a disaccharide. Invertase from the yeast breaks them up into glucose and fructose. So why is it doing that? Well, first of all, it likes to use them itself. So the yeast then takes that fructose and glucose and is able to further metabolize it. And its output, oxidizing it, basically burning it for fuel. The output is carbon dioxide, just like the output that you and I have when we burn fuel in our bodies, like we breathe out carbon dioxide. But it also makes ethanol. The bacteria like what they see here. They're digging this. So the bacteria take up the glucose and fructose, the excess glucose and fructose that the yeast are liberating with their invertase, and they do a number of things. They make a cellulose mat out of the glucose. So cellulose is just a long chain polymer of glucose molecules that are linked with what's called a beta-1,4 linkage. You'll learn about that in the carbohydrate unit. They make glucuronic and glucuronic, various varieties of acidic versions of glucose. And then they also take up the ethanol that the yeast has been producing, and they convert that to acetic acid. All right. So all of that gives the kombucha the particular qualities that we've become familiar with. So this is a symbiosis. It's a cooperative process in that there is this group or shared public goods here, right? Where the both the yeast and the bacteria, it's in their best interest to break the sucrose down using the yeast's invertase into glucose and fructose. Some of that gets fermented into ethanol by the yeast. That is used by the bacteria and turned into acetic acid. Both the ethanol and the acetic acid, so first of all, the bacteria taking the ethanol and making acetic acid out of it, that is kind of a waste removal thing. It's breaking ethanol, which is the waste product from the yeast, and turning it into acetic acid, which is not as harsh an environment to live in for either of the two microorganisms. And these syntrophic interactions, that just simply means that both the yeast and the bacteria are happy to use the glucose and the fructose, and then the ethanol is further metabolized by the bacteria. There are these different levels in the community, in the microbial community, that are using a shared resource. The bacteria make the cellulosic mat, which is the pellicle that forms on the top of the kombucha. That is the spatial structuring, right? It's spatial structuring where you are able to have this three-dimensional network of cellulose that is invested with the yeast and the bacteria. It helps. And then in terms of competition, excluding other bacteria, excluding other molds or microorganisms that are going to be wanting that sugar that's in the solution. Well, first of all, the ethanol and the acetic acid, that inhibits invaders because other organisms don't want to live in that. And then this cellulosic mat, besides being a spatial, like a high-rise apartment for these microorganisms, it's also a physical barrier. It's a physical barrier to other stuff getting in to the sugary broth that's below. This also helps to block access to oxygen, keeping it in this sort of anaerobic fermentive conditions down in the SCOBY, down in the broth that is fermenting. So this is how the yeast and the bacteria work together to create this cooperative environment that allows them to both benefit to the exclusion of other microorganisms. Kikuli's blown away. Wow, cool. But you must make proteins too. Where do you get your nitrogen? We haven't seen any nitrogen. Scoby's glad you asked that question, Kikuli. These are some nitrogen-containing compounds that are in tea and are essential. So if I were to ask you what's in black tea, you'd all probably say caffeine. Probably wouldn't say theanine, but that's in there too and does have nitrogen. Both of them are nitrogen-containing. The kombucha itself, when you drink it, the final brew, is actually pretty low in caffeine because all that caffeine is consumed and utilized by the SCOBY. The SCOBY's trying to extract that nitrogen and use it for its own purposes. Yeah, so SCOBY says, nothing like a caffeine fix. He prefers Irish breakfast tea, personally. Actually, it grows just fine with any kind of black tea. All right, so kombucha. I hope after this talk you've come to love or at least appreciate some aspects of it. Kikuli is convinced of the properties, the beneficial properties of kombucha, but a little skeptical of public displays of affection with a person's SCOBY. The SCOBY itself is just feeling the love. Okay, thank you. That's all I got. Bye.